To show you how current limiting works on this drive, I put a large 12-pound steel sprocket on this motor to give us some inertia to overcome. I reset the drive to factory default and set up the motor parameters to match this motor and set the reference frequency to 60 Hz to tell the drive to ramp up the motor to full speed over the acceleration time we specified. The acceleration ramp is currently at the default 5 seconds, which is a good place for us to start. And I'll reduce the deceleration ramp time to 4 seconds so we're not spending a lot of time waiting on the motor to decelerate. I'm using the free WPS software and this USB COM module to talk to my drive from my PC. I've already created a configuration and a resource, and I'm online with the drive. Now we're just going to use the WPS software to visualize things. I'll enter the parameters from the drive's built-in HMI as a reminder that we don't need the free WPS software and optional USB COM card to do this. Speaking of visualizing things, look at this. Down here under Protections, Inverter, these graphs show us exactly how limiting works. This side is voltage limiting. We cover that in a different video. And this is the current limiting that we're doing in this video. The current limiting threshold is in parameter 135. That threshold can be used for 3 things. First, it can be used to disable current limiting. If we set the threshold really high, the manual says to set it to 1.9 times the drive's max rated current, then there won't be any current limiting. Let's try it. This drive is rated for 4.2 amps, so I'll go to parameter 135 and enter 8 amps. I'm also going to go to parameter 100 to set the acceleration ramp at a ridiculously small number to really stress the drive. Hit run, and of course we get an overcurrent fault. The second current limiting option is to set the threshold at a reasonable value and employ one of 2 current limiting techniques. The default current limiting threshold for this drive is 6.3 amps, about 50% above the drive's max rated current of 4.2 amps. Now remember, the drive's max rated current is how much current the drive can handle continuously. This threshold is looking for spikes in current. If we go to the data sheet, we see this drive can handle 150% overload for 60 seconds and 200% overload for 3 seconds. So a 6.3 amp threshold makes sense. Okay, given that threshold, we have 2 choices. One is if the current hits the threshold, have the acceleration ramp hold to give the motor a chance to catch up. Remember, it's the acceleration of the motor that creates the demand for the current. The greater the acceleration, the more current it needs. So if the drive holds the ramp constant until the motor catches up, then the current demand falls. The other current limit option is when the motor current hits the threshold, instead of holding the acceleration ramp rate, it actually allows it to decelerate until the motor catches up. In both cases, once the motor catches up, the original ramp continues on. So what these are really doing is automatically extending the ramp time to prevent an overcurrent fault. You could accomplish the same thing yourself just by using a longer ramp time, but then you would have to figure out how long that needs to be. By using the current limiting options, you're letting the drive give you the best possible ramp time automatically. Let's do an example so we can see how this works. Now I would love to show you this in the WPS trend view, but trend view isn't really fast enough to show us what we need to see. Its fastest sample rate is only 50 milliseconds. So instead, I'm going to use this optional I/O module that has 2 analog outputs, and we'll send the motor current and the output frequency to those 2 outputs so we can view them on a scope. If I look in the programming manual's analog output function table, we see output current is a 5, and output speed, which they call the real speed, is a 2. So I'll go to parameter 251 for analog output 1's function and enter a 2 for real speed, and go to parameter 254 for analog output 2's function and enter a 5 for the output current. I'm monitoring those on an inexpensive USB oscilloscope I bought on the internet. Okay, before we change anything, let's get a baseline. Let's get the acceleration ramp back to a reasonable 5 seconds and put the overcurrent threshold back at the default value for this drive, which is 6.3 amps. I'll get the scope running and hit run on the drive. Wait the 5 seconds for it to ramp up, give it a couple more seconds to settle out, and then hit stop. Cool. We can see the red frequency ramp is pretty much what we expected. and the drive was able to get the motor up to speed in the 5 seconds we wanted. And most important, the current looks good. The analog current output is 0 to 10 volts, where 10 volts is twice the drive's rated current of 4.2 amps. How did I know that? It's in this analog output table in the programming manual, where parameter 295 is the drive's rated current, which means the current got up to around 3.2 amps. And we know from parameter 135 that the current overload threshold is set at 6.3 amps. So since the current never got anywhere near that level, it says the 5-second ramp was easy for the drive to do. So let's challenge the drive by going to parameter 100 and reducing the acceleration ramp to a ridiculously small time to really stress the drive. Start to scope, hit run, stop. Let's zoom in so we can see this better. Now the motor current is crossing the threshold and the ramp is getting extended, but it's kind of hard to see, so I'll speed up the scope and let's go to parameter 135 and lower the current limit threshold to exaggerate the effect. On our baseline, we saw the current never got above 3.2 amps, so I'll lower the threshold to something just above that. How about 3.6 amps? Again, you wouldn't normally do this. I'm just doing it to get current limiting to kick in sooner so we can see the effect a little better. Start to scope, hit run, stop. Our new current limit threshold is here at 3.6 amps. Now the bad news is it looks like the drive is only updating the analog output every 25 milliseconds, so we get this stair-step effect instead of a smooth curve. Which means we have to use our imaginations a little bit and just know that there are some fast transitions here that we can't see on this plot. But we can see the end result. The frequency output is definitely going into that ramp deceleration mode in several places to extend the ramp time and prevent an overcurrent fault. Looks like the 0.1 second ramp time we asked for was extended to a little over 1.5 seconds. Let's go to parameter 150 and switch from ramp decel to ramp hold mode by putting a 2 here. Start to scope, hit run, stop. And we got pretty much the same ramp time, but this time, instead of decelerating the ramp to limit the current draw, it was simply held level, exactly what we wanted. And again, while the analog output is too coarse to see the actual threshold crossings, we can definitely see the ramp hold periods and that the current was held at a reasonable level. Okay, well, while we're at it, let's see what an overcurrent fault looks like. I'll go back to parameter 135 and put it at 8 amps again to turn off current limiting. Start the scope, hit run, stop. Well, that was pretty quick. We put the overcurrent threshold way up here, and sure enough, the motor current was allowed to spike, and in a little over 100 milliseconds, the drive shut the output down. Cool. The bottom line is, if you're getting an overcurrent fault like this, you probably have the current limiting threshold set too high, and the fault is kicking in before the limiting can take effect. Setting that overcurrent limiting threshold to a value that works best for your application is usually the key to fixing an overcurrent fault issue. And a good starting point is about 150% of the drive's max rated current, which is the default value for these drives. Click here to learn more about the WEG CFW300 variable frequency drive. Click here to learn about Automation Direct's free award-winning support options, and click here to subscribe to our YouTube channel so you'll be notified when we publish new videos.